This is a calm explanation of how scientists currently understand time. There is no single definition that fully captures what time is. Instead, time is something we describe through how it behaves. This video is not meant to rush toward answers. It's meant to slowly explore what we know, what we measure, and where our understanding breaks down. In everyday life, time feels obvious. Seconds pass, minutes follow, events occur in sequence. But in science, time is not treated as a flowing substance. Instead, time is measured by change. We define time by comparing repeating processes, like the vibration of atoms or the motion of planets, and counting how many cycles occur. Clocks do not measure time directly. They measure regular motion. Time, in physics, is the framework that allows events to be ordered. In classical physics, time and space were considered separate. Space described where something was. Time described when it happened, but modern physics treats them differently. According to relativity, space and time are linked. Together, they form what scientists call space-time. This means time is not universal in the way we once believed. Different observers can experience different amounts of time between the same events. One of the most surprising consequences of relativity is time dilation. Time does not pass at the same rate everywhere. When an object moves very fast, time passes more slowly for that object relative to a stationary observer. The same is true near massive objects. Strong gravity slows the passage of time. This has been measured directly. Clocks placed on satellites tick slightly faster than clocks on Earth because they experience weaker gravity. Time, it turns out, depends on motion and mass. At human speeds and scales, time dilation is extremely small. The differences only become noticeable when dealing with objects moving near the speed of light or extremely strong gravitational fields. That's why time feels stable in daily life. But stability does not mean simplicity. It just means the effects cancel out in ordinary conditions. One of the deepest questions about time is why it seems to move in one direction. We remember the past. We do not remember the future. Broken objects do not spontaneously reassemble. Heat flows from hot to cold. This direction is called the arrow of time, but most fundamental physical laws do not prefer a direction. They work the same forward and backward. The arrow of time emerges from something else. That something else is entropy. Entropy is a measure of how many possible arrangements a system can have. Systems naturally move from ordered states to disordered ones because there are far more disordered configurations. This statistical tendency gives time its direction. The past had lower entropy. The future has higher entropy. Time appears to move forward because disorder increases. This leads to a difficult question. Why was the universe in a low entropy state to begin with? At the earliest moments of the universe, conditions were highly ordered. This initial state set the direction of time for everything that followed. But we don't know why it started that way. This is one of the deepest unsolved problems in physics. Another question often asked is whether time actually flows. Physics equations do not describe time as flowing. They treat time as a dimension, similar to space, where events are located. The sensation of flow may be a feature of human perception, not a property of time itself. From this perspective, past, present, and future all exist as part of a larger structure. We experience them sequentially because of how memory and consciousness work. Time is closely tied to cause and effect. Causes come before effects. This ordering is fundamental to how the universe behaves. In physics, causality limits what can influence what. Signals cannot travel faster than light. This ensures that cause precedes effect for all observers. Time structure preserves consistency in the universe. At very small scales, our understanding of time becomes less clear. Quantum mechanics treats time differently than space. In many quantum equations, time is not an observable, it is an external parameter. This creates tension between quantum mechanics and relativity. A complete theory that unifies both does not yet exist. Some theories suggest time could behave differently in extreme conditions. Near black holes, time slows dramatically. In some models of the universe, time could stretch indefinitely. In others, it could reach boundaries we do not yet understand. At present, we don't know whether time had a beginning in the way we imagine, or whether it could have an end. Despite centuries of study, major questions remain. We don't know why time has one direction, why entropy started low, whether time is fundamental or emergent, how time fits into a quantum theory of gravity. These questions are not failures. They mark the edges of current understanding. Time governs every process we observe, yet its nature remains deeply mysterious. We measure it, we experience it, we depend on it, but we still don't fully understand what it is. As with much of the universe, time reveals patterns without revealing its origin. And for now, that uncertainty is part of the structure of reality itself.